Hi everybody, I hope this video finds you well. In today's video, we're going to be starting on the last hypothesis test that we'll be talking about in our term. This hypothesis test is called the analysis of variance test and is often abbreviated as ANOVA. This ANOVA test is another example of a global hypothesis test. And it is used when you want to investigate if there is a difference amongst 3 or more population averages based on 3 or more samples of quantitative data. This analysis of variance test basically brings us sort of full circle from where we started. If you guys remember when we first introduced hypothesis testing and confidence intervals, we started with a single sample of quantitative data. And since then, we've built from there into several samples of quantitative data, 2 sample means and matched pairs. Then we moved into dealing with categorical data, again with 1 sample or 2 sample of categorical data. More recently, we've been doing chi-square tests where we were looking at the distribution of a categorical variable or the relationship between 2 categorical variables. Now we're finally ready to sort of return to quantitative analysis and talk about what to do when you have 3 or more samples of quantitative data. So this is the ANOVA test. Now we're going to run through, again, as always, the sort of 5 main components of this hypothesis test, and then we'll get into an example of running it. So let's talk about the hypotheses. So the null hypothesis is that the population averages are all going to be equal. So in other words, if you have several different populations, your baseline or null assumption is going to be that the average for each population is equivalent. We write that as mu1 equals mu2 equals mu3, and then if there were more than 3, you would have equals mu4 equals mu5, etc. If there's only 3, then you would just cut that right there and have mu1 equals mu2 equals mu3. But I'm just leaving it open with that ... in case you had more than 3 populations. What's the alternate going to be? Well, this is a global hypothesis test, so the alternate is very general. It just says that at least one population average is different from the others. Now, this alternate could mean a lot of different things. This could mean that mu1 and mu2 and mu3 are all different from each other. It could mean that mu1 and mu2 are the same, but mu3 is different. It could mean mu1 and mu3 are the same, but mu2 is different. Or it could mean that mu2 and mu3 are the same, but mu1 is different. So again, this alternate is global, right? It's very general here. It's just saying at least one of the averages is different from the others. Let's talk about the conditions. The conditions are sort of unique here because unlike every other hypothesis test we've done so far, there are actually 4 conditions here. The first 3 conditions are the very standard ones for when working with quantitative information. First, we have to have all the samples be random and representative. That's very standard. All the samples must be less than 5% of their respective population sizes. Again, very standard. All samples must be approximately normal or size greater than or equal to 30. This condition 3 is the standard condition 3 when working with quantitative data. Your data either has to look approximately normal or there has to be greater than or equal to 30 data points in each sample so that we can use the central limit theorem. Now, condition 4 is sort of an interesting condition. Condition 4 says that all populations have the same standard deviation. Now, this is a very easy condition to state, but if you think about it, it's a very hard one to confirm because to confirm it in reality, you'd have to know the population standard deviation. Yet, whenever we're working with data, we know that we only have a sample, not a full population. So we don't get to know what the population standard deviation is. So we have sort of a way of checking that this 4th condition is reasonable. And what we do is we check this 4th condition by confirming that the largest of the sample standard deviations, the maximum of the sample standard deviations, is smaller than 2 times the minimum of the sample standard deviations. So in other words, what we're doing in condition 4 is we're making sure that the smallest sample standard deviation isn't that much smaller than the largest one, which if all the sample standard deviations are reasonably close to each other, it's reasonable then to say that all the population standard deviations are close to each other. Now, as it'll turn out, the majority of your guys' work when running an ANOVA test is going to be in checking these 4 conditions, and we'll see that in our next example. The reason why I say that the majority of your work are going to be in those checking those conditions is because for steps 3 and 4, you'll notice I've sort of combined them together, the test statistic and p-value, because we're going to be using the calculator exclusively to actually calculate this. We're not going to learn a formula or look at a statistical table because actually trying to compute the ANOVA test statistic by hand is very, very messy. So instead, we're going to be using our calculator. So how do we use our calculator to do this? Well, what you're going to do is you're going to first put each sample into its own list. So the first sample will go into L1, second sample will go into L2, third sample will go into L3, so on and so forth. Then you will use your stat key, which is what you would normally use. But in the past, when we've hit stat, we've used both edit and calc. Now we're going to go to the third option, which says tests. Once you're in the tests menu, you're going to scroll through all of the tests until you find the ANOVA test. The ANOVA test should generally be at the bottom of that list. Once you have the ANOVA test, you'll go ahead and hit enter, and then it'll give you an ANOVA prompt. And then inside the parentheses it gives you, you'll want to type in L1, comma L2, comma L3. If L3 is your last list, then you'll just end with a parentheses. If there's other lists, then you'll have to do comma L4, comma L5, etc. Then close up the parentheses and hit enter, and the calculator will give you the test statistic, which in this case is an F statistic, and the p-value. So there won't be any formula that you'll need to plug into. The calculator will take care of both the test statistic and the p-value for you. But just to be consistent, we will want to record both of those. Then, finally, in the conclusion, we make the conclusion just as we always have. If the p-value that the calculator gives you is smaller than alpha, then we will go ahead and reject HO, and we will have evidence that at least one of the populations has a different average than the others. If the p-value is greater than alpha, we will fail to reject HO, which means that we will not have any evidence that any of the population averages are different from one another. Okay, so just to recap here, because this is sort of unique, the ANOVA test is sort of right at the border between introductory hypothesis testing, which is pretty much everything else we've been doing, and more advanced hypothesis testing. The more advanced hypothesis tests become, the more and more complicated they become to do by hand. Doesn't mean that they can't be done by hand, but it becomes very messy, very time-consuming. As you guys already have seen, calculating just even the chi-squareds, the independence and homogeneity and the goodness of fit, oftentimes have lots of computations. The ANOVA is one that is right at that sort of borderline, and we're going to be using our calculator to take care of this computation completely. That means when you guys are carrying out an ANOVA test, the majority of the work is going to be on confirming those conditions. Once you get to steps 3 and 4, it's just going to be typing stuff into the calculator and then recording both the F statistic and the p-value. So let's jump into an example and actually see how this works. So, for our example here, we're going to suppose you want to study if the average SAT score differs between students from California, Oregon, and Washington. So what you do is you randomly select some students from each state and you record their SAT scores. So you get the following data. So you had a student from California who got a 970, a 1050, an 1110, so on. In Oregon, you had a student who got a 960, all the way up to a student who got a 1510. In Washington, you had somebody who got an 870, all the way up to a 1390. What we're going to do in part A is we're going to carry out at alpha equals 0.05 a hypothesis test to test the claim that there is a difference in the average SAT score between California, Oregon, and Washington. Then, as a follow-up in part B, we're going to build a 95% confidence interval for the average SAT score just for students in California. So let's start with A here and talk about what type of hypothesis test this is going to be. Well, notice that there's the mention of the word average in the actual question and back up here when we're talking about what we're actually studying, average SAT scores. Also notice that all the data is quantitative, right? The different students that you selected, you recorded a quantitative piece of information. So we certainly know that we're studying a quantitative variable here. How many populations do we have? Well, how many samples do we have? Well, we've got one sample for California, one for Oregon, and one for Washington. So we have 3 or more samples of quantitative data. That tells us that this is going to be an ANOVA hypothesis test. 3 or more samples of quantitative data. So we know that this is going to be an ANOVA hypothesis test. Let's go ahead then and set up the hypotheses. So, for the hypotheses, the null hypothesis is going to be that the averages for each population are equal. We can do a little bit of sort of notation. We can say that the average for California is going to be the same as the average for Oregon, is going to be the same as the average for Washington. So the averages for each population are equivalent. What is the alternate going to be? Well, the alternate is that at least one population average is different. Now, again, there are lots of different possibilities for what it means for at least one to be different. Could mean that California is different from Oregon and Washington. Could mean that California, Oregon, and Washington are all different, or some other combination. But again, this is just a global test that's saying that there's at least some difference amongst the three populations. All right, let's go ahead then and move on to the conditions. So, condition 1, all the samples need to be random and representative, and that was stated by saying that we randomly selected the students. Then we need all sample to be less than 5% of their population size. Well, we got 3 different populations here, so let's make sure we state those. So we'd say lots of California students, check. Lots of Oregon students or Oregonian students, and lots of Washington or Washingtonian students, I suppose. So we know that our samples are very small in comparison to the amount of California, Oregon, or Washington students. So we know condition 2 is satisfied. What about condition 3? Well, if we look at our samples, it looks like for California, we had like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 students. Oregon, we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And Washington, we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we had 11, 11, and 12. None of them are over size 30, so we're going to have to confirm that each one is approximately normal. So that means we're going to have to do 3 stem and leaf plots here. So we need all the data, all samples, let's say it that way, that'll make it a little clearer. All samples need to be approximately normal. So let's start with California. For California, it looks like we had things like some 900s in the thousands all the way up to the 14. Now notice we don't really need to plot the last digit because it's always 0. So it looks like we can have stems starting from 9, 10, 11, 12, 13, and 14. Then for the 9, we'll have 9, 7. For the 10, we'll have that 10, 50. For the 11, we'll have the 11, 10, and the 11, 40. So 11, 10, and 11, 40. For the 1200, we'll have the 12, 20, 12, 30, 12, 50, 12, 50, and 12, 70. So that sounds like 2, 3, 5, 5, 7. So 2, 3, 5, 5, 7. For the 13, we have that 13, 40. Is that correct? 1360, excuse me. Let's just correct that there. 1360. And then finally 1480. Okay. Is that perfectly normal? Certainly not. But does it look good enough? Yep. There's no strong skew, no outliers. We're all good there. So no strong skew, no outliers. So we're all good. Let's go ahead and look at the data for Oregon. All right. For Oregon, looks like we'll have to have stems from 9 up to 15 this time. So we'll have 9, 10, 11, 12, 13, 14, and 15. For Oregon, it looks like we have 9, 6, then 10, 8, then 11, 5, then 12, 1230, 1230, and 1260. So 1200, 1230, 1230, and 1260. Then looks like 1320 and 1340, 1320, 1340, and then 1450 and 1510. So again, not perfect, but generally got our peak in the middle, got tails basically out to both sides. So we'd say no strong skew and no outliers. So we're all good there. Finally, we can go ahead and do the data from Washington. Looks like we'll need a stem of 8 up to a stem of 13. So we'll have 8, 9, 10, 11, 12, and 13. And looks like we've got 870, then we've got 920 and 960, then 1030, 1080, so 31st, and then 80, and then 11, 40, 50, 60, and 70, so 4, 5, 6, 7. And then we've got our 1220 and 1270, and then we've got our 1390. And that also has no strong skew. That one looks very nice and symmetric, and no outliers. Now, since these were stem and leaf plots, we probably should have a key, but notice that I used the same structure for all of them. So we can just include one key. We can say like 9/7 here actually means 970, and that applies to all three, so we're all good there. Well, that was a lot of work because we had to do 3 separate stem and leaf plots. Unfortunately, we're still not done with the conditions. We now need to check condition 4. So for condition 4, we need to check that the max sample standard deviation is less than 2 times the minimum sample standard deviation. Well, at this point, if you need to calculate these standard deviations, it's probably time to go ahead and put this data into your calculator. You need to do that anyway to run the ANOVA test, so now is a good time to do so. So let's go ahead and put the California data into L1, the Oregon data into L2, and the Washington data into L3. Then, since we need to know the standard deviations, let's use our 1var stat on each of the lists. So let's go ahead and get our data in there. So for California, we have 970, 1050, 1110, 1140, 1220, 1230, 1250, 1250, 1270, 1360, 1480, and we're all good. We should have 11 data points in there. Okay, for the Oregon data set, which we will put into L2, 960, 1080, 1150, 1200, 1230, 1230 again, 1260, 1320, 1340, 1450, 1510, again 11 data points. And then finally for the Washington data set, looks like we've got 870, 920, 960, 1030, 1080, 1140, 1150, 1160, 1170, 1220, 1270, 1390, got 12 data points in there. Okay, now we're going to use our 1var stat on each list separately. So for L1, technically for this step, you only need the standard deviations, but it does not hurt to record the averages and the sample sizes, because if we do need to build any confidence intervals, like we do in B, it's probably a good idea to have those. So let's record what we get for each one. For our first sample, for the Californians, looks like X bar should be approximately 1211. I'll just skip the decimals since the numbers are very large here. And it looks like, actually it'd be 1212 once we round. Looks like the S is going to be 142, and the N in this case was 11. Now do your 1var stats on L2 as well, and record that. So for Oregon, the average was 1248. The standard deviation was 157, and the N was 11. And then finally, 1var stats, but now with L3. And we can calculate that. Looks like the X bar here is going to be 1113 with a standard deviation of 150 and an N of 12. So we're just going to record that information just in case we need it for later. Technically for step 4, you just need these sample standard deviations, but doesn't hurt to write it all down since we already typed it in. All right, so which of these had the largest sample standard deviation? Well, it was our sample from Oregon, where the sample standard deviation was 157. So we'll check, is 157 less than 2 times the minimum one? Well, the minimum sample standard deviation came from the sample from California, where we got a 142. So we can just check 157, is that less than 2 times 142? 2 times 142 is 284. 157 is less than 284, so we're all good. So all 4 conditions have been satisfied here. All right, now we're ready to do steps 3 and 4 together, which is the test statistic and p-value. In every other hypothesis test, you guys do these separately because they each have their own components. But since we're going to be using the calculator to do this, we can do it all at once. So since we only had 3 samples, we will just need to use the ANOVA of L1, L2, L3, close up the parentheses. Do make sure that when you type this in, and again, remember that ANOVA comes from stat, tests, and then find the ANOVA function. You want to make sure that you do put those commas in between L1 and L2 and L2 and L3. Once you do that, so go across, hit stat, then go across to tests, then go all the way down until you find the ANOVA test. Usually it's near the bottom. then type in L1, comma, L2, comma, L3, close up the parentheses and hit enter. You'll want to record two things. The F statistic, which in this case looks to be approximately 2.52. It's the first thing that the calculator tells us. And the p-value, which is the second thing the calculator tells us, which would be 0.0971. And we will usually just record this to 4 decimal points. You could round it more if you wanted to, but just for accuracy, might as well put 4 there. All right. The calculator gives you a bunch of other stuff, which is used for more advanced analysis with the ANOVA, but we won't be using it, so just record these two things. Then we go to our conclusion step. As always, we take our p-value, which of course is this 0.0971, so about 9.7%. We compare it against the alpha, which is 0.05. Clearly, the p-value here is larger than alpha, so we will fail to reject HO, right? Because we had a p-value that was larger than our alpha. So we have no significant evidence for our claim. What was our claim? Well, our claim that was at least one of these populations had a different average. So no significant evidence that there is a difference in average SAT score between California, Oregon, and Washington. Now, again, what are we really doing? What is this test really doing behind the scenes? Well, clearly, as we saw from our calculations here, our sample of Oregonian students had the highest average at 1248, and the group from Washington had the lowest at 1113. But we are saying that these values here are not different enough, given the amount of variation that we expect to see, to say that there's really a fundamental population difference here. That's what this test is really doing. So there's no reason to say that students from California, students from Oregon, or students from Washington perform on average differently on the SAT. Notice again that when we are writing this conclusion, since we are back to talking about quantitative data, we are very careful about specifying average, since that's what we're studying here. All right, so this is our first example of running one of these ANOVA tests. Let's, as a quick follow-up and a little bit of review, build a 95% confidence interval for the average SAT score for just students in California. So we'll go ahead and do that on our next page here. So for part B, we'd like to do a 95% confidence interval for average SAT score for California students. All right, we know that this is a confidence interval, so we got to figure out which one. We haven't learned any new ones, so it's got to be one of our older ones. For confidence intervals for quantitative data, we had the 1 sample mean, 2 sample mean, and matched pairs. Well, since we're only looking at California students, this is only going to be a 1 sample. So this is a 1 sample mean confidence interval. This was actually the very first type of confidence interval we learned, so this is a good piece of review here. What about the conditions? Well, the conditions for a 1 sample mean confidence interval: random and representative, sample less than 5% of the population, data approximately normal, or 30 or more data points. Those are all things we've already checked because we checked them for all the samples, so we can say already checked. So we're all good there. Then we can move on to the construction. What's our formula for a 1 sample mean confidence interval? Well, it's x bar plus or minus t star s over root n. So there's 4 things that we need to know here: x bar, s, n, and t star. Well, the average here would represent average for the California students. We actually already calculated that. That's back when we used the L1 data here, and we got an average of 1212, standard deviation of 142, and we know the n is 11. So let's fill all that stuff in. Our average is 1212, our standard deviation 142, I believe that's what we said, yep, and our sample size is 11. How do we get this t star? Well, you might say 95%, isn't it 1.96? That would be z star. T star, we have to use table C and know some degrees of freedom here. So the degrees of freedom, sample size 11, going to be 11 minus 1 equals 10. We're going to do 95% confidence and intersect those two. Let's go ahead and take a look at that on table C. So we've got 95% confidence, 10 degrees of freedom, intersect those, looks like we have 2.228 as our t star. So we have 2.228 T star 2.228. So let's go ahead and fill this stuff in. 1212 plus or minus 2.228, 142 over the square root of 11. Then we go ahead and calculate this. So this would be 2.228 times 142 divided by the square root of 11. So that would give us 1212 plus or minus, I'll just keep one decimal here, 95.4. Then let's go ahead and do our subtraction and then our addition. So if we do the subtraction, we should get 1116.6. And if we do the addition, we should get 1307.4. Then we would write our interpretation. We'd say that we're 95% confident that the average SAT score for California students is between 1116.6 and 1307.4. There we go. And that's our range for what we think the average SAT student score for California students is between. Somewhere between 1116.6 and 1307.4. Does that mean that that's where 95% of California students land? Absolutely not. This is just an interval for the average SAT score for California students. So there we go. In this video then, we've seen our first example of this new and final hypothesis test, the ANOVA hypothesis test. And now you guys have done a quick review on the original confidence interval. You learned the one sample mean confidence interval. In our next video, which will be the very last of our lecture videos, we will take a look at one more example of running the ANOVA test.